Hello. In the previous video, I explained the basic underlying concept of sampling distribution. So the previous slide, this slide is what I made. I added this slide to the authors, the textbook slide. And the authors use sampling uncertainty, which is basically the same thing, the same idea, because the key idea is that the experiment is the sampling. So we are going to sample again and again. If that is repeated, what will be the distribution? That's the idea. So the uncertainty, the randomness is coming from, the sampling. And what can we do? What can you do with the sampling distribution? We are going to do the same thing as we did with the sample mean. So for example, we are going to do some hypothesis testing. For example, most commonly used hypothesis testing is to test if beta 1 is 0. So does the student-teacher ratio has any effect on the test score? If you believe no, then this is the hypothesis. So a student-teacher ratio has no effect on test score, can be formulated into this hypothesis. Or you may construct a confidence interval for your estimator beta 1. So confidence interval is the interval you believe that the true value lies in. So it's also a useful approach to use the sampling distribution. And we are going to go into the details of the sampling distribution. So let's think about the probability framework. The assumptions we need is like this. First, you have to define the population. What is the group of interest? In our example, I think the corresponding population must be California state's school districts, because all the school districts in our data are from California. So basically the population that we can study from the data is the Californian school districts. And once you define the population, then you random sample and observe random variables, y and x, test score, student-to-teacher ratio. So you have to define what variables you are going to use in the regression model. Of course, it's your choice. Of course, you want to include relevant variables and reasonable variables. And we need to make some assumptions on the data and the distribution. Underlying distribution, the joint distribution of those variables, should satisfy these. First, their relationship should be linear. So linear, this is why we call the model as the linear regression model. So we can make it nonlinear, but that will make the model more complicated. So we are going to restrict our attention to linear models. And linear models are still useful enough and general enough and widely used in the frontier research. So linear regression model is simple but very powerful and can handle a lot of problems. So we don't worry too much about linear assumptions. And second assumption is the conditional mean zero assumption. So the error term should be on average 0 regardless of x. So no matter what x is, your error term has to be unbiased, or it should be 0. And the third assumption we need is non-zero finite fourth moment, which means there are not too many outliers. If x and y have too many outliers, then it causes problem. Or if the distribution of x and y have thick tails, too thick, then it has problems. And finally, IID assumption, which is very important. but a very fundamental assumption. So under those assumptions, this is the statistical setup we can study, under which we can study the sampling distribution. Then the sampling, from the sampling distribution, we would like to do what we'd like to calculate what is the mean. So if the mean of the estimator is the true slope beta 1, then you can say that the OLS estimator is unbiased. Of course, we know that it is unbiased, and so it is good. It satisfies at least the first condition to be a good estimator. And second, we would like to calculate the variance of the estimator, which is a measure of uncertainty or a measure of accuracy, how reliable your estimator is. And usually, after taking the square root of this variance, we call that the result as the standard error. So standard error is literally how much error you have to expect from the estimator. And then we will study the distribution of beta 1 hat. In other words, so it says in small samples, in large samples, but we are going to ignore a small sample case because it's very complicated, and in most cases our samples are large enough, like more than 100, 200, still good enough. So we are going to rely on the central limit theorem and normal approximation, assuming that, under the assumption that the sample size is large. Then in large samples, beta 1 hat is normally distributed, which is really nice. And in other words, why is it nice? Because it's not only about the estimator, but also maybe it is more intuitive to understand. So we are interested in the estimation errors. So then but we cannot, from one estimation, you don't know, to calculate the estimation error, you should know the true parameter. Without knowing the true parameter, you cannot calculate the estimation error itself. However, we can calculate the distribution of the estimation error using the sampling distribution theory, using the central limit theorem. So later on, you will see that what it means is that the estimation error is normally distributed. So it's distributed around 0 and with a nice tails go to 0 quickly enough. So which is what we desire. Anyhow, we cannot eliminate the estimation errors. So then we have to live with it. Then it's better to we need to know the distribution of that. That is provided by the sampling distribution of beta hat. This is the objectives of the sampling distribution analysis. And from now on, in the next, you will see, warning, you will see a lot of mathematical equations. But don't worry, I'm going to skip most of them. If you are interested, I would be really happy to help you with mathematics. But the main focus of this course is rather on programming and writing and more practical purpose rather than mathematical derivation or proofs. So I will really quickly go through those mathematics. So please let me know if you are disappointed by my skip, and if you are interested, I'm really happy to talk with you and to help you. So please let me know. I will. So I'm going to do that in the next video. I'll see you later.